So where I had left off is we had this circuit. We had these little leads here. This was kind of our innovation, and this is actually called a commutator, where this part that's connected to our rotating piece, that's the commutator, and these are the brushes. So they kind of, you can imagine, you could design them as brushes that always stay in touch, kind of like the brushes on what was that? What are those cars at the amusement park? Bumper cars, right? On the bumper cars, you have a pole behind your bumper car. I'll draw that for fun. So let's say this is your bumper car. Looks like a shoe a little bit. This is you driving your bumper car. And they have a pole, and at the top of the pole, you'll see these brushes that are touching the ceiling, right? You could view that as the same type of brush. So what it allows is a constant electric current to flow through the ceiling. I'm assuming, I don't know what direction it's going in, but it allows a current to flow through the ceiling, and maybe your car is grounded so the current can flow down to ground, so that your car could be powered by the ceiling and not have to carry a battery in every car, which would be kind of a waste of energy and probably some type of a health hazard and safety risk, etc., etc. So those brushes on your bumper cars might not be all that different from the brushes that are touching the commutators here. Just a little bit of terminology, and never hurts to introduce bumper car references. Probably should have done them earlier when we were learning about momentum and things. But anyway, so what was happening here? So going back to our first video, we have the current going down like this. And then if you use your right-hand rule with the cross product, you know that the net force from the magnetic field is going to be downwards on the left-hand side, upward on the right-hand side. So you have a net torque rotating it like that, rotating the right out of the page, the left into the page or into the video screen, up to the point that you've rotated 90 degrees, and now you're looking kind of, so this side right here, let me do it in a different color so you can see it. This side is this side, right on top, and this side is on bottom, below the page. This side is now above the page, right? If this distance is r, this side is now r units above the page. And I said, ideally, maybe your commutator loses touch with the brushes at this point, right? Because they're popping out a little bit, so when you're vertical, they actually lose touch with the brushes. So you have no circuit flowing, so you save a little battery energy, and you just let a little bit of the angular momentum carry this whole rotating contraption further a little bit, to the point that your configuration will look like this. So I know I keep changing colors, but where the whole contraption will now look like this. Will now, okay. That's my positive, negative, positive, negative. Current flows like this. Now, we assume that the commutator has gotten back in touch. And let me color code this. So if this side is this color, right? Then this side, now this is when we're looking at top on, where it's popping out of the screen, where it's above the screen. And now we've rotated 180 degrees, and this side is on this side, right? And if this side, let me pick a suitable color. If this side was green, now this side, we flipped the whole thing over 180 degrees. Now something interesting happens. Remember, before we had this commutator and everything, if we just flipped it over, the current, because before when we didn't have the commutator, the current here was flowing up, was flowing down here, up here. And before the commutator, we had the current flowing down here and up here, and so we were switching directions. And so you would have had this thing that would never completely rotate. It would just keep flipping over, right? Which may be useful for, I don't know, if you wanted to flip things. But it's not useful as a motor. So what happens here? Now this side, all of a sudden, instead of being connected to this lead, is now connected to this lead. And this green side is now connected to this lead. So something interesting happens. Now the current on the left side is still flowing down, right? And the current on the right side is still flowing up. So we're back to this configuration, except that this contraption has flipped over. The brown side is now on the left, and the green side is now on the right. And what that allows is that those net torques are still going in that same rotational direction. Use your right-hand rule. The current is flowing down here. So if your magnetic field is coming to the left, then the net force is going to be down there, and it's going to be up there. And so we can continue indefinite, and we solve our other problem, that we will never keep twisting these wires here. So now, using the commutator, we have essentially created an electric motor. And remember, I drew that little thing. That could be like the axle. Maybe that turns the wheels or something. So if you have a constant magnetic field, And you just by using this commutator, which as soon as you get to that kind of vertical point, it cuts the current, and then when you go a little bit past vertical, a little bit past 90 degrees, it switches the direction of the current. So on the left-hand side, you always have the current coming down, and on the right-hand side, you always have the current going up, so that the net torque is always going to be rotating this contraption down on the left-hand side and up on the right-hand side. Coming out of the page on the right-hand side and then down on the left-hand side. And you could actually turn a wheel now. You could create an electric car. So that is the basics, really, of how electric motors are created. I mean, most electric... Well, there's another way you could have done it. You didn't have to use the commutator. One methodology you could have used is you could have had the magnetic field going until you get to this point, and then you turn off the magnetic field, right? And maybe you wait for this situation to go all the way 180 degrees, and then you turn the magnetic field back on again, right? That's one possibility, but that's maybe not as efficient because half of the cycle you're not powering it. Or maybe you switch the direction of the magnetic field. Or another option, you don't have to use a commutator. Maybe you use some other contraption to switch the direction of a magnetic field. But this is probably the simplest way to do it, and I think it gives you a general idea of how an electric motor can be created, and then we could play around with the mechanics of innovations on it. But all electric motors are essentially some variation of what you have learned in this video. Isn't it neat to learn something useful? See you in the next video.